Hi everyone, welcome back to Primitive Computing. We're going to have another episode tonight where I'm going to do some more work on trying to build a computer operating system and programming language and just the whole computing environment from scratch, starting with nothing but an assembler. If you can remember from the last couple of weeks, we've mostly been looking at the boot sector and with Pong. And so today we're going to pick up where we left off and start making some progress toward the higher level programming language, and so that I don't have to be writing an assembly language the whole time. So this is going back kind of in history to, people ask the question like, what language did you write the first programming language in? Or not me, I didn't write the first programming language, of course, but when people say, how do you make a programming language? It's like, well, you write it with another language. You write an interpreter or a compiler or whatever. But if you have no programming language already to start with, how do you uh, get one? It's like a chicken and egg problem, Well, we have a programming language that we're working with already, and that's called assembler. But the nice thing about this one is that it's built directly into the CPU, and so that means that like we basically don't need anything besides the CPU. We don't need another existing language. We're cheating a little bit because we have an assembler already, and the assembler is written in a programming language. It's like programming languages all the way down. So, yeah, we're doing that. Eventually we'll write the assembler too, and then we can just kind of be completely self-hosting. And I guess, if you really wanted to ask the question, how would you get started if you had no programming language at all? Like, we would need a different kind of input device. Like basically we could assemble the code by hand. So all the assembler does is it looks at things like, I have my code up here where, it has this instruction move comma 3, 3 hex or 3 decimal, they're the same. But anyway, so if you go look in like the Intel rules or the Intel like software developers manual, it has rules for how to take all of these instructions, like this move instruction, and to encode it into a binary format that the CPU understands. So if you wanted to, you could just painstakingly get out a sheet of paper in the Intel software developers manual and go through and assemble this all by hand into binary code. But then we still need a way to get it into the computer itself. And then for that, like, the old computers used to have toggle switches where you could just flip little switches on the front of the panel and load programs that way. Or, if you had a punch card computer, I imagine you could actually like punch the punch cards yourself, but we're not going back that far. We're starting with an assembler and because it's kind of about as small as you can reasonably get, and then we're going to build from there, and then eventually we'll, like as I said before, we'll write the assembler and continue. So if you remember, never mind, I forgot what I was going to say. Lost my train of thought there. So anyway, let's pick up where we were before. Let me show you what we got to. First, I'm going to make a new branch for tonight's episode. So tonight's episode 4. So we have that. I'm keeping each of these episodes in a different branch. So if you ever want to go back and see what what I did in each of the episodes, you can go and see, step by step, basically. So this will all be in GitHub afterwards. So I encourage you to go check it out and leave comments or, pick up the code and play with it on your own. So I can run this in QEMU, and it always opens up on the wrong screen. But when I pull it up on there, here is my Pong game that I've been working on for a while. Whoops. There's a small little bug I should fix, but I'm not going to worry about that. We've written Pong in assembly. The first day we fit it all in the boot sector, and then last week we wrote it in the second sector in the disk, and then we wrote some code to load that out. And the nice thing about that is it means that because we can now load code off disk, we're no longer limited to just a single sector. So we're essentially, and we're not actually unlimited in code size right now, but we're, compared to what we were, we essentially are. And I think it'll be a while before we hit the limits that we're at. So, there you go. So that's where we were. I'm gonna pull up the README, and I may or may not. Actually, let me make a new file here called goals. So we'll save this as goals.md. So let's see. So today it's February 7th, 2021. Whoops, that's a lot of, there we go, 2021. So the goals are going to be, so our main goal is to do what's called a prefix arithmetic calculator. Arithmetic calculator. Sometimes I call it an evaluator or an interpreter, or you know, whatever you want to call it, but I'll call it a calculator for now. I'll say a little bit more about what that is in a second, but I just want to throw that up there, that's our main goal for tonight. The second goal then is to, so there's, I guess what I mean is not necessarily the second goal, but there's some other things we can do in support of this goal. So one of those is to be able to print out numbers. That should hopefully be easy, and in fact in most languages it's built in, but we're an assembly language still, so we don't have that ability. So we need a way to print numbers, and that's mainly just because I want to be able to tell if the program printed out the right answer. Okay. And then maybe, I don't know if we'll get to this tonight or not, but we also want to be able to parse numbers or parse input. We probably will, but I guess what format the input actually takes is kind of an open question. So the easiest thing is we can just write our input as a string constant in the file and then evaluate it directly. If we weren't in a language that wasn't assembly, like that had an optimizing compiler, it would probably just go and optimize that into a constant. But the assembler doesn't do stuff like that for us. So we'll probably start by doing that, just writing the input into as a string constant in the program. But we could also read it from the keyboard. So, and if we do that, we really will have taken our first step towards having an interactive programming language, because we can, we'll be able to type expressions into the computer and get an answer out. So it's kind of the very simplest form of computing. So what do I mean by prefix arithmetic? So there's normally, when we write math expressions, we write them in what's called infix. So like 1 + 2, and that equals 3. And what we mean by infix is that the operator, in this case plus, comes in between its operands. So plus, or 1 and 2 in this case. So if the operator comes in between the two operands, that's called infix. But there's other ways you can write math as well. So one way is called prefix, which is what we're going to be using tonight. So for prefix, you would write it as +1, 2, like this. Oops, there we go. Let me indent it so that the highlighting looks the way we want it to. Actually, I'll do it in like code fences. There we go. Cool. Yeah, actually no, never mind. I'm changing my mind again. So this is infix, this is prefix, and then that would mean that, so what prefix means is that the operator comes first, and so we read in a plus, and we read in a number and another number, and then we want to then have the program print out the answer to this number. So in this case, this would be 3 again. And if you have infix, you have prefix, and it's also, I'll just go ahead and mention this, there's something called postfix, which is also kind of common. And postfix, so we had infix was the operator comes in between, and prefix, the operator comes before or pre, it's a prefix to the expression. And postfix, it comes afterwards. So we would have our two operands first, and then we'd have plus, like that. So what that means is it says, you have an operand, and then this says add the previous two operands together and then get the result. And so that would be a 3 as well. So why am I writing math in a funny way? You can do it either in prefix or, I mean, yeah, I could do it in any of these 3 ways to do it. The cool thing about prefix and postfix is that you don't need parentheses at all in it. And so like, say I wanted to do something in infix, like, I wanted to do like 1 + 2, whoops, and then multiply that by 3. I have to add the parentheses or we have to worry about order of operations and, which like operator precedence and all that. So by the normal, like if I just wrote this without any parentheses, I would get 2 times 3, I would do that first, and then I would add 1 to that, so you get 7. But if I put it in parentheses, then that says do the 1 plus 3 first, and then multiply it by 3. But the cool thing is if I write this out as prefix, I am explicit about what order you do the operations in. So I'll do it in postfix first, actually, just because that I think will make a little bit more sense. So postfix is you want to take 1 and 2 and add them together, and then you want to multiply that by 3. Okay. Prefix is going to be similar, so we want to multiply 3 by the result of adding 1 and 2 together. So we do plus 1 and 2 like that. All three of these say the same thing. These should all evaluate to 9, but it's mostly just the order of how you rate them. Both prefix and postfix are cool because they don't need any grouping, any operator precedence or anything like that. And since we're in a really simple language right now, we don't want to spend a lot of time with operator precedence. That gets annoying. It's if you take a compiler's course, at least a lot of them are like, it seems like the whole class is about parsing, and a lot of that is just because of all the complexity around infix or not infix, but like order of operations and precedence and all that stuff. So I don't want to mess with that tonight. I want to do something simple, and I'm going to do prefix because I like it. The other reason for choosing prefix for me is that this is actually the format that like Scheme and Lisp use for their code, I guess, for lack of a better word. So and I'm if you followed any of my other work, I do a lot of Scheme. I'm a big fan of Scheme. It's a simple language, at least in my mind. It's a simple language to work with. And in particular, it's a simple language to implement. And that's really, if we're trying to bootstrap a system and get it self-hosting as fast as possible, we want a language that is easy to implement. So anyway, so that's my little bit about prefix arithmetic and what it is. We'll see more of it as we go through it. But, as I said, the first thing we need to do is we need to parse some numbers. So let me go back and start writing some code. No, not parsing numbers. Sorry, we want to print numbers. So we had our boot sector before, and I'm going to basically wait. Yeah. Okay, here it is. Cool. So this is these first 40 lines of code or so are the boot sector. So let me add some more comments to just make this really clear. So I'll say begin boot sector. And then we're gonna say down here we'll have end boot sector. So that, see, I always forget where that is. I should just make these separate files, but then I don't know why I said sugar either. When you type and talk at the same time, I get my words mixed up. So, this can be kind of embarrassing when you're doing it live on YouTube, but that's part of the fun, right? Anyway, so there's the end of the boot sector. We can basically just leave this unchanged tonight, so we don't really need to do anything on it. We actually could delete this section right here because that's printing out some text that you're not even going to be able to see. We may actually remove it later, but I'll leave it there for now. And then down here we have Pong. So it's not going to be Pong anymore. I'm just going to call it main because we can use main pretty much forever after this. And this code we can just delete all of it. I don't think we'll need it. So this is, I think tonight will be the last night that we saw. Well, probably not. Pong's going to come back, but we're probably not going to see it in a while. We did see some at the beginning, so it's not completely without Pong tonight, but we're getting there. So, Cool. So let's make sure this works so far. The first thing I always do is make an infinite loop, and that is I don't know. That's just like the easiest program to write when you don't have any operating system or anything. So I'll do now. Whoops, not boot that ZSM, boot that ASM. Oh, right. I'll just call this main. We'll jump to main, and there we go. So let's run it. Whoops, gotta grab my QEMU window. So we have our hello world. That was from our boot sector. And there we go. Looks good so far. So now that we've got that in there, let's start printing a number out. So let me see. So here's what we're gonna do for printing numbers. Okay. Typically the okay, I'm gonna go back to our goals. Maybe I should have called this notes, but oh well. So I'll start a new section here for printing numbers. In a language like C or C++ or whatever, what you would normally do is you write the okay, so basically the idea is first you want to get your digits. So like you do that by taking your number mod 10, and that tells you like the smallest digit, and then you take your number divided by 10 again, and then you just repeat this, and that gives you each of your digits. But the problem is it gives it to you from the smallest digits to the highest digits. And so like if I took a number like 1, 2, 3, 4, 5, and then I did this like in a loop down here, what I would end up with is like the first digit that I get would be 5, then 4, then 3, then 2, then 1. So if I print them in order, I would get 5, 4, 3, 2, 1. And that's not what I want. So there's a couple of things we can do. One is we could like write it out as a string and then reverse it. So that's always an option that we can do. But another thing we can do is use recursion and kind of do this backwards. So we can sort of traverse down and get the numbers that we need, and then as we come back out, we can print them out. And we may even be able to cheat a little bit and just like use the stack. I think that might actually work pretty well for us. I'm thinking about the stack right now. Yeah, I think that should actually work. If like does it work? Okay, so what we would do is we would, yeah, this will work. So what we would do is we would push 5, then 4, then 3, then 2, then 1 onto the stack. Then we see we have a 0, so like that means we're at the end. And then maybe we can keep track of how many numbers that we have on there, and then we can just pop off. So we pop when we print 1, then 2, then 3, then 4, then 5, and that works. This is basically like doing it with recursion, but we don't actually have to do the recursive calls. We can just do it with a bunch of jumps. So let's stop deleting all my notes here. So that's what we're gonna do for this. Okay, so we're gonna make a function called print number, and we actually are gonna borrow some stuff from up here because we're gonna need the cursor position. So we'll just go ahead and get the cursor position to start with. Actually, we're going to do that later, but we will need this code. And then let me just go ahead and add the comment from up here as well. Okay, we'll need that later. Okay, let's add a thing on here. So let's see, prints a number in decimal. And so our arguments are going to be RAX is going to get the number to print. Okay. So it should be pretty straightforward. So it prints a number in decimal at the current, cursor position. I don't know if we want current cursor position or if we want to actually just like send that in. I don't know. Whatever. We'll think about this some more as we go. So the first thing we do is RAX is going to be the number. So we will do we'll test RAX with RAX. Sorry, not RAX. I'm using RAX. Those are the 64-bit registers, and we're still in 16-bit mode. So we don't have access to those. We can just do AX. I think we can actually use the 32-bit registers and maybe even the 64-bit ones because we're emulating a 64-bit CPU, and I think that there's like bit size overrides that make that work. But let's sort of stay true to the form here and stick with a single or just stick with the 16-bit registers. So let's see. So if it's 0, let's do we'll just do a special case of printing 0. So let's see. So 0, we jump to print 0. And then that we'll stick down here. So for this, we'll just push 0, and then this is going to be where we actually do the printing. So basically, the idea is we're gonna push all the numbers onto the stack, and then when we get to 0, we jump down to this print stack, which is where we'll actually do the printing the numbers. Okay. So now we come in here and we okay. So I'm gonna need to go do some reading. So let's do Intel assembly reference. Let me find a good reference here. There's like one I always use, but I never think to like bookmark it. Yeah, this is one that I like. So we're gonna use the mod instruction, but I want to check like how that actually works. There may not actually even be a mod instruction. I think it might be yeah, there's not a mod instruction. I think it's div actually does it. Let's check. Okay, so here we go. So divide the unsigned value in whatever our arguments are. So either AX, DXAX, EDX, EAX, or RDX, RAX by the source operand, the divisor. And so the divisor, I think, yeah, it can be a register or memory. I think it can be can it be an immediate also? Let's see. And so stores result in AX or DXAX or EDX, EAX. Let's see. Cool. So our operand size will have so we have a double word or word, and then we have a quotient, and then the remainder, maximum quotient. Okay, cool. So this is what I was wondering about, which is that AX and DX are going to have the quotient and the remainder. So anyway, that's cool. We don't have to do both. So what we want to do is we're gonna, I think let me see if div10 works. Let me nasm. Oh yeah, we need colons there. Okay, so we do need to move into bx. Let's move 10. And then we're gonna divide by bx. Okay. So this says divides. Oh yeah. We want to zero out dx also. Okay. So this divides dx ax by bx. Stores quotient and ax. And let me make sure that's right. Yes, it divides that. So quotient goes into ax and then the remainder goes in dx. Okay. I'm actually going to move the zeroing part down, and I think that'll be apparent in a second. Is that right? Yeah, that's right. Okay, cool. So then the remainder is going to be that's the mod. So that's the what's left over from the division. So we divide it by 10. That's going to be what's in this position. So we're going to push dx. Actually, you know what? Let's push dl, because we know because we're dividing by 10, the remainder is always going to be in it's going to be less than 10, which means it'll definitely be less than a byte. So that should be fine. Down here, we should do push byte. Actually, maybe we can divide by 10. Let me try again. Let's try div 10. Whoops. So let's see, there's a couple of problems. So 65 and 66 are giving us. Okay, I guess we have to push dx. And then we're gonna, let me say div byte 10. No. Okay, so we do actually have to divide by registers. Division ends up being a tricky instruction in a lot of CPUs. Some CPUs just don't even have a divide, and you have to write a library to do it. I'm glad we don't have to worry about that, but whatever. So, okay, so this is save current digit to the stack. And then, okay, so we push dx, and then let's do test ax. J not 0 back to let's say loop, or let's see, div loop, because we're probably going to need more than one loop. Oh, I always forget the colon up there too. So div loop. Okay, cool. So not 0, that means we've still got further to go. If it is 0, then we also want to okay, up here we want to 0 out cx. We're also gonna have to remember to save all our registers at the end of this too. So you know, okay. This is not going to be push byte anymore. So it's going to be push word 0, and then we're gonna move into cx1. Here we're gonna add cx1. So this will be how many things are on the stack. Okay, cool. Once we get down to 0, that means we've pushed all the digits onto the stack. And so then we are going to print the stack. So we'll do jump to print stack. So the first thing we do is we get the cursor position, and I'm gonna try something. Actually, I don't know. Let me check out the so the interrupt 10h. with AH equal to 13. So let me pull up my, here's my new Ralph Brown's interrupt list. Actually, no, let me go to this one. Yeah, let's try this one. So we're going to look at interrupt 10 with 13 for AH, and then we have right string. Returns nothing, notes. So what I'm wondering is, does this leave the DH DL with the updated cursor position? Because that would be really handy if it did. It doesn't say that it does, but let's try it out and see. Let's try that. Okay. So we have the cursor position, and then we're going to print. Actually, I'm gonna push these as characters. So let me say, after we have the current, okay, before we have the current, let's add dx the character 0. So basically these are going to be ASCII characters that we're pushing onto the stack, and then that makes it easier down here to print them. So this is going to be our print loop. So we will, let's see, we'll test CX with CX. I wonder if Intel has like a ret Z instruction. That would be, I don't know. I'm just going to make an exit label down here. And so here we return. We're going to need to restore our stack and make sure that's all set, but whatever. Okay. Oh man. I think, oh no, we can't do it because we're pushing words on, not bytes. I wish we could just push a byte. That would be really nice. Can't we? Let's check. Oh yeah, we can only push words, double words, or quad words onto the stack. That's annoying. Whatever. Anyway. Okay. So we test CX. If it's 0, we go down to exit, and otherwise we continue. So let's see. Here you go. Let's pull our, yeah, I think this should actually be pretty straightforward. Okay, so here's our print a string with interrupt 10h. So for this, let's see, we move AH into there. Honestly, we can do this up here. That's fine. AL, yeah, that can stay the same too, because we're going to use that. BL, I think that's just the text and stuff, so that's fine. Oh no. Okay, let me go read some more about this interrupt list. Oops, that's not the one I want. I want this one. Close that one, get it out of the way. Here's what we can do. So what I'm going to do is there's this option here where we alternate strings, or alternating characters and attributes. Okay. So instead of pushing Okay, so what I'm going to do here is we're going to move into DH the attribute, which will be 7F in hex. Let me do it like that. I think that's what we were doing down here. Or just 7H. Yeah, 7H, that's what we want. It's the 0. I'll do it at 7H. Okay, so we put that in there, and then here let me move into let's see, move into DH 7H, and then move into DL just the character 0, and then we're going to push DX. I could have like done this by hand as a constant, but I didn't want to mess with that. So actually, I'm not even sure we can push a constant. So, there we go. Okay, cool. So now we don't even need this loop here at all, to be honest, because let's see, CX is going to have the size, and what is it? CX is the number of characters in the string. Cool. So for AL, the write mode, we now want to use, instead of using 0 for AL, we're going to use 1. Okay, so we get the cursor position. What? Oh, yeah. Okay. Whoops. I just like messed all that up. Okay, there we go. Yeah, we don't need this print loop at all. So we have the, okay, cool. So we're gonna use 13H again. AL is gonna be right. What? That's weird. Before I said, oh yeah. So we set the update cursor after writing bit. We also want to set the we want to say we're alternating characters and attributes. So we have to add 2 to this, so we get 3. So it's going to be update cursor after rating, and so I'm going to say and then 2 is going to be, I don't know, do 0x1 cursor rating, and this is going to be 2 bytes per. Okay, so we have 2 bytes per character in input. What that means is we're alternating the number of we're alternating characters and attributes, so this would let us print like multicolored numbers if we wanted to. That might actually be kind of fun, but I'm not going to worry about that right now. So CX, by the end of this loop, we already have the number of characters in there, so we don't have to worry about that. And so what we do want to do is move into our base pointer. We want to move the stack pointer in. So basically the stack is now pointing to a string. Since the string grows downwards, or the stack grows downwards, we've been pushing the characters basically in reverse order. So now on the stack, we have the string already in the nice format that we need. And so this should just work if we're lucky. Let's try it out and see. Okay, so we have our main loop here. You know what, let me rename this to loop. So here we're gonna move into AX. Let's do 100, 1, 2, 3, 4, 5. Yeah, that'll fit. And then we're gonna say call print number. So when I run this, what we should see is hello world from the boot sector. And let me change that string actually. And instead of hello world, it's gonna be hello from the boot. There we go. Cool. So what we should see is we should see hello from the boot sector, and then we should see 1, 2, 3, 4, 5 show up on there if it assembles. Loop is inconsistently redefined. Oh yeah. Yeah, we aren't allowed to like jump between sections. That's part of the issue or problem with trying to have the whole, basically the whole disk image in a single file. We eventually we're going to want to be able to split this up into multiple files. Let's run it, and okay, well that's interesting. We have hello from the boot sector, and then we have something happened here. So I wonder what went wrong. We did end up with the cursor all the way down at the bottom. That's a little bit interesting, but yeah. Okay, let's try some debugging. Um, let me see. Oh. We probably screwed up the stack, so who knows where we return to. So we're gonna save the stack pointer into the base pointer. Um, oh no. Ugh. Here we go. Okay. First thing we're gonna do is push the stack pointer. So basically, I'm rediscovering the function prologue. If you ever look at code generated by like your C compiler, the first instructions of most functions look sort of like this. And this is basically creating a stack frame. So what I'm doing is I need to know my stack pointer because that's how I know how to find my way back to the program that I started in. And then I'm going to save the current stack pointer in the base pointer. Oh, this is still going to break. Um, no. So okay. Why am I doing this again? What am I doing? No, we're not going to do that. So anyway, the problem is I think I just lost my stack pointer. So then when I tried to return, I returned to garbage memory, and it looks like the machine crashed or something. Um, we don't have a debugger hooked up, so this is kind of like real life. We can't really see what happened without that. Um, okay, here we go. We know how many bytes we popped onto this or we pushed onto the stack. So what we can do when we get down to here, so we wanna fix the stack and return. So we know CX holds how many digits we pushed on there. It was 2 bytes per digit. So let's multiply. We shouldn't. Let's not multiply. Let's use a shift. In a way, this is like premature optimization, but it's also it saves us some registers, multiplies a really expensive instruction. It's whatever. We're just gonna do. Oh yeah, this is cool. There's even like an opcode here for multiply by 2, which is what I want to do. So we're gonna say shift. Oh yeah, there's like shift associative or shift arithmetic and shift logical. Um, let me. I always forget the difference between shift left and I think for left shift it probably doesn't matter, but if it did, I feel like they wouldn't have given us 2 instructions. So we have shift left and right, and then we have different shift left and right. So here we go. The arithmetic shift left and logical shift left perform the same instruction. Okay, so yeah, they actually do the same thing. Um, oh, that's cool. It actually shifts a bit in the carry flag. That's going to be handy. Okay, cool. Um, yeah, okay. So it doesn't matter. I'm doing shift left. It doesn't matter if I do cell or shell. but I'm going to do SHL. So we're going to CX2 or 1, I mean. So, okay, and that multiplies CX by 2 bytes. And then we want to add this to the stack pointer, and this should get us back to where we were. So let's add SP CX. So let's boot that again, and let's run it. And there we go. The same thing as before. Interesting. So let's try some other stuff out. First, let's try printing out 0. Like 0 should just work. So let's try that. Nope, we get the same thing for 0 also. So that's interesting. We do have hello from the boot sector. We did end up way down there somehow. I don't really know why that happened. Okay. Okay, so I'm staring at my code trying to figure out what's going wrong. So we XOR 0. We're not saving any registers here, but it doesn't matter because we're not using any of them later, so that's fine. We check for if it's 0. If it is 0, we go down to print 0. Otherwise we gotta print, and there we just fall through to print stack. So here, if AX is not 0, we go back up to div loop, and then we 0 out DX. And that's just to make sure that we don't, like divide anything else into it. And then we divide dx ax by bx. We store the quotient in ax and the remainder in dx. So for dx, we add 0 to it, the character 0 anyway, and then we move so that should be fine. Push dx and add cx to 1, or move in cx1. Add cx. So we push dx and then we move. Okay, that gives us the cursor position, and then we want to print. Okay, I'm gonna try one more. Let's try 1. And so I pull that back up here so you can see it, and still nothing. So that's interesting. You know, the interesting thing, let me pull that back up here again, is that for some reason the cursor has ended up down there, and that's weird. I don't know why it's ending up down there. It should have been here, and then yeah, so it should have been right here, and then we should have printed out a couple of words. It's almost like we're printing out way too many words for some reason. I wonder if I'm doing something wrong with my dividing. Like, I don't know. That's weird. Okay. Let me try just doing nothing here first. Okay. So when I pull it up like that, we do end up with the cursor right there. And so somehow we're doing something to move the cursor. Where was it? It was like right down there, kind of towards the bottom. So something's happening. Let me try just. Um, okay. We'll call this exit. And so now instead of printing the stack, I'm going to try just jumping to exit. Okay. So I want to see if we skip that part, do we still get weird behavior? And we don't. So that's looking good. Okay, what if I move this down? So load the cursor position and run it. And then, so we still get the right behavior. We get hello from the boot sector and then something there. So here's where we actually want to print the string out, and we can just get rid of the jump to exit. And this is not going to work because, well, that's interesting. Maybe I forgot to compile it. I think that's what happened. Nope. Well, that's interesting. Oh, maybe I'm not calling the. Oh, yeah, that's the problem. There it is. Yeah, no wonder that wasn't doing anything. It was yeah. Oops. I wasn't calling my function at all. So print 0 now we're gonna, or print stack, we're gonna say jump to the end. Try that. Okay, so that's looking good. So we said jump to the end, and nothing happened. So that means this loop up here isn't corrupting anything. So that's good. Let's skip our first interrupt and try again. So, okay, we're still good. We still have the cursor where it's supposed to go. Let me go one. Let's go down to here then. I'll leave the jump this time. It doesn't hurt anything. Just waste some a few CPU cycles. Okay, so now we get that weird thing where we've ended up printing down really far. So that's kind of interesting. Yeah, that's weird. And it's weird that it's always the same. So let's try something else then. Let's here we go. We're gonna move AXBP. Then we're going to move BPSP. And then we're going to push SP. So that's how we can get our stack pointer back. So we don't want to do that there. And here we want to pop SP. Yeah, because we're not using AX here. There's our base pointer and our stack pointer. Actually, I'm going to push CX. And here we're going to pop CX. No, actually, we do it. Yeah. Okay, what did I just do? So let me try a different way of doing this stack thing. So I think we can do similar, like swizzling around different things. So let's let's move into the BP SP. We probably want to save that, but oh well, I'm not going to worry about it. So then down here, before we overwrite BP, where's the part where we overwrite BP? Great. I guess we want to do it. Okay, so there we go. We get the cursor thing. We want to move into BP, the stack pointer. So this is where we're going to be printing from. But the first thing we want to do is move into AX, our base pointer. And then, okay, then we move into BP, the stack pointer, and then we push AX. Okay, then we do our interrupt. And then we want to, so here, yeah, we pushed AX, we want to pop BP. And then down here, instead of doing this, we're just going to move. So at the very beginning, we moved our stack pointer into the base pointer. And then we do some juggling around here to save the base pointer. And so here we're going to move base or into the stack pointer, the base pointer. Let's try that. I don't think this is going to fix it, but hopefully it doesn't get worse. Well, we end up with kind of the same thing, but the nice thing about this is now we don't depend on CX. So what I want to try doing is, instead of using our count from up above, I want to try moving into CX. Let's try moving 1. So let's try printing just a single character and see what we get. Okay, so we print a single character and we get a blank. So that's kind of weird. We should have had a 1 on there, but we didn't. Let me change this to be 0. Let's make sure we can print 0 to start with. Whoops. Okay, 0. Here we go. Okay, so somehow we're printing like way more characters than we should, which is kind of weird. This writing from the stack doesn't seem to be working. Maybe, or okay, let's try. Let's see. OSDev wiki memory map. I bet our stack's in the wrong spot. I bet that's part of it. Nope, doesn't say anything about stack, so who knows where the stack is. But okay, so for writing a character, oh, ESBP is the string to write. So let's move our stack segment into ES. Whoops. Yes. Oh, did not mean to launch QEMU again. Let's go back. Oh yeah, we can't move directly between the segment selectors. That's kind of annoying. So here we go. We're gonna move into AX, the stack segment, and then we'll move into ES, AX. I think this should work. Okay, that was the problem. So now we have 0. That's looking good. We printed out 0. Great. Which is a single character. So now let's try not printing out the character or the count there. So we should still get 0. Let's see what happens. Oh, that's That's really bizarre. So we did get a 0. We just printed out a bunch of other stuff. So I'm really curious now what's going on there. Like, why did that happen? Maybe something is overwriting CX. I bet that's it. So maybe getting the cursor position overwrites CX. Let's find out. So cursor position is 3H on that. There we go. Let's try that. Yeah, get video cursor position and size. Oh, yeah, that's what's happening. We're returning the scan line in CX. So we want to let's push CX, and then down here we'll pop CX. And I bet that'll fix it. Okay, okay. So there we go. We printed out a 0. Yes, progress. Now let's try printing out a different number. Let's try printing out 1. And here we go. So that worked. We printed out 1. Now let's see if we've really solved the problem by printing out a longer number. So we'll try this. We get 1, 2, 3, 4, 5. Great. Nice. And then since I wouldn't be a real programmer if I didn't print out the answer to life, the universe, and everything, here we go. Let's make sure that one works too, and it does. So cool. Yeah, that's kind of cool. That worked. We got it working. It returns fine. We get into our infinite loop. We're seeing all the stuff we want to see. So, yeah, it's kind of sad that took an hour to print the number out onto the screen, but it's working. So yeah, I don't know that there's any anything. Oh yeah, I want to make sure I clean this up. So let's make sure we save all our registers to here that we clobber, just to make sure we're good citizens. I'm gonna use a calling convention where basically you can assume that like basically everything is going to be called esave. So we can pass arguments in registers, but I want to make it so that the callee can basically has to pretend as if it never ran. So this means we need to push BP, and then down here we need to pop BP right before the return. We have to like yeah, duplicate these. I'm gonna open up my boot.asm over here as well, because I want to be able to see both. I want to make sure I'm doing these in the same order, or the right order. Okay, so there's where we save our stack pointer. Yeah, we're gonna push CX because I see we use that. We're gonna push AX. I'm sure we use BX also. And DX we use. We also clobber the extra segment, ES. Yeah, we clobber ES also. So let's make sure to push ES too. Okay, and then down here we need to fix the second returns. We pop BP. Okay, I'm gonna go from the bottom up now. So we have pop ES, pop DX, pop CX, pop EX, pop AX, and then we pop BP too. We already had that in there. NASM, run it, and then we still ended up printing 42, so that's looking pretty good. So cool. Okay, cool. I'm gonna look real quickly in our assembly reference over here, because when I was searching for push, there's also push A and push AD. So let's check out push A and push AD. So hey, there's a couple of other registers I could have used. So there's push A, which pushes all the general purpose registers. So that's, you know, AX, CX, DX, and BX, which we were going to do. And then also SP, BP, SI, and DI. So basically everything except for the segment registers. So, you know, we could have done that, but I kind of like just having it written as a, you know, written out like that. So we know exactly what it's doing. So I think I'm going to leave it like that. And that looks good. So cool. Well, anyway, we've been able to print out numbers. I'll put out the proof on the screen again, and there we go. So this is why people don't write assembly anymore, is because it takes forever to do trivial things like this. So we you know, I'm coding at this for an hour, and we printed out a number. So I didn't get quite as far as I wanted to tonight, but I also think that it's going to get longer to get through the prefix calculator than I want to spend tonight working on this. So I'm going to go ahead and wrap things up now. The next time we get back to this is you can pick up where we left off and try and get the prefix arithmetic calculator going, or maybe do number parsing instead. It should get faster. You know, I'm not really, like, I don't write assembly language all day long, so I'm learning a lot as we go. And you know, as I'm writing more complex assembly language programs, I should be able to write more complex ones as well in shorter amounts of time. So, you know, we learned a lot this time. At least I learned a lot. I hope you learned a lot too. And we'll pick this up the next time we do this. I've been doing these about once a week, these live streams. Next week is Valentine's Day, and so I don't really spend, like, I feel like spending my Valentine's Day evening coding in front of a computer and talking to a computer. So we'll probably take next week off, but then we'll definitely come back to this and pick up with the prefix arithmetic calculator. So once again, thanks everyone for watching, and I hope you learned something. I know I definitely learned something from this process, and I will see you when we see you again. So stay tuned for next time. Thanks.